Hi, my name is Dr. Stephen McGee. I'm the president of the Learning Partnership, and I'm here to introduce our inaugural webinar address for our webinar series related to Journey Tel Yunque. Journey Tel Yunque is a web-based curriculum program that focuses on introducing students to long-term ecological research being done in Puerto Rico around the El Yunque rainforest. Our inaugural address was actually done last week at a workshop in Chicago with 17 middle school science teachers in the Chicago Public Schools. And my colleague, Dr. Jess Zimmerman from the University of Puerto Rico, delivered that address to the teachers through the video conferencing system. So I'm going to allow him to introduce himself, introduce us to the talk, and then we'll pick up the webinar midstream. Jess?
Okay, I'll share my screen and go over here and start the talk. So the talk I prepared for the workshop was one based on our project we call the Canopy trimming experiment, which is Canopy trimming experiment is designed to simulate some of the more important effects of hurricanes on a tropical rainforest and provide some context for Journey Tel Yunque, which is about hurricane effects on some of the major species in the rainforest. I started out the talk by talking about whether hurricane frequency is on the rise in the Atlantic basin. This is due to a couple of things. The first I discussed was natural long-term cycles in hurricane activity. It was recognized beginning in the mid-90s that there were influences of weather from Africa on the rate of formation of tropical hurricanes. And so there's a natural cycling that started into a high phase in the mid-90s, explaining why we didn't really observe very many hurricanes during the 60s, 70s, and 80s. And so there are natural cycles in hurricane frequency, and we continue to be in a high one. Now, when the tape picks up, I'll talk about global climate change and how that affects tropical cyclone frequency. The other thing is global warming, which is supposed to affect sea surface temperatures. And basically, one effect of sea surface temperature is that you don't have a sea surface temperature of 26.5 degrees Celsius or higher. Hurricanes won't form. I mean, there's other things that are going on, but that's a major one. And so people were pointing out that if the global warming is real, that sea surface temperatures are going to become higher, and that's going to make hurricanes more frequent. And so that was the other justification for doing an experiment. So to this day, we continue in a natural high period of hurricane frequency. And the discussion of how global warming is predicted to affect hurricane frequency has gotten very sophisticated. There's certain patterns of weather that occur that are predicted to occur with global warming that will actually discourage the formation of hurricanes. And so what we've ended up with is a slightly complicated prediction that what's going to happen is that when we get hurricanes, because of the high sea surface temperatures, they're going to be very intense ones. And so if you know the Saffir-Simpson scale that they talk about on the news all the time, we're predicting that the frequency of hurricanes is going to shift into category 4 and 5 storms, like the Katrinas and the Ritas that occurred in 2005 or 2004. I can't remember that. But anyway, very big storms when they happen. So the basic intensity of the hurricanes is going to increase. So you've studied or looked at the perspective of hurricanes from the Keys. When we first summarized our understanding of these things, we created the graph down below. And I don't know, Stephen, can they see the cursor as well as I can?
Yeah.
Okay. So there's a number of graphs here that show on the bottom you have years since Hurricane Hugo, basically from 0 to 5 years since Hurricane Hugo. And then we just looked at the change in magnitude of some critical things that we had studied. And your coquilles that you've looked at today are line B. And that is that they went up after the hurricane and then they went back to normal after a few years. Um, the number of shrimps in our streams did exactly the same thing. They had the same pattern. They rose and then fell, and we're still not exactly sure why that was. Um, Not as well studied as our coquilles. Um, Things like stream nitrate and potassium, which come off the decomposition of all the debris or detritus that's been dumped on the forest floor by the hurricane removing the branches, uh, peaks very early on. I lost my cursor. Peaks early on. That's curve A. And then curve C, D, E, and F are different species of invertebrates, mostly land snails and a walking stick studied by our colleague Michael Willig at the University of Connecticut. And they do very interesting things. Their numbers go down very much right after the hurricane, and then they start to recover, sometimes going over the numbers that we consider reference numbers or normal numbers, and sometimes remaining well below that. And walking sticks, we have these wonderful species, big species of walking sticks. They used to be very abundant before Hurricane Hugo. Their numbers have never recovered. And this is another area that we don't understand, but it's a pattern that we can identify. Um, as you can see on the right here, what we identified early on is the kind of the key factors that happen in a hurricane, at least for above ground sorts of animals and processes. Was one is here's a picture looking beyond the gate at our field station after Hurricane Hugo. You can see that much of the canopy has been removed from this forest. The individual crowns of the trees have been broken. The branches have been broken off. Um, you can see one tree fall in there, but it's mostly not whole trees falling down like we know is important in, say, in storms in New England or other parts of the world. It's just that all the branches are broken off. And then all that detritus or plant debris is then piles on the ground. And if you capture one of the important aspects of the response of a coquille frog to um, this pattern of damage is they actually like all that debris because it's places they can hide. But we really don't know what the negative effects of the canopy opening that occurs simultaneously because they occur simultaneously. And so it's very difficult watching how things change after a hurricane to disentangle these two important effects. And the only way you can do that is in an experimental setting. And this is where it gets kind of crazy. So what we did was, this is a layout of the canopy trimming experiment. Um, there's This is our field station where we do all of our work in the lower left-hand corner. There's a series of trails that take you out to the experiment. There's a large plot in the middle. It's called the Luquillo Forest Dynamics plot, where we monitor forest dynamics without any manipulation. And around this, we placed three replicates, or blocks we call them, where we did four different things. We left the forest. These are 30 by 30 meter plots, which is 100 feet on a side, let's say. So fairly large, about the size of a gap that's formed in a hurricane or tree fall. And so we left one set of plots as control plots that we did nothing to except monitor the way the forest functioned. And we simulated a hurricane by trimming the canopy just like a hurricane does. We did this with arborists. I'll show you some pictures. We trimmed the canopy, all the major branches, and then placed that detritus or debris on the forest floor just like would happen in a regular hurricane. And then we disentangled these two things, and this is the crazy part of this. We actually trimmed some large plots and removed that detritus, physically carried it away from the plot to an untrimmed plot and put the detritus on the ground. So we could simulate the effects of just what's happening with the detritus or debris on the ground and just with the canopy opening. And this is called a factorial experiment because you're separating the different factors that you think are important, and you look at them, with no effect, with the individual effects and then with the combined effects. And it turns out in nature, you get the combined effects, and it's these individualized effects that we're interested in. Okay. Are there any questions in the room at this point? This is pretty dull science up to here. All right. Okay. So, but before we did any of the treatments, we did two. Pardon?
Jess, can you go back to that slide?
Yeah.
So I did want to point out the LFDP, the Luquillo Forest Dynamics plot. So that's actually the plot where the Coqui data was collected from. So when it says from a plot of this size, it was actually that plot. And so that's one in which no humans actually go in and explore that. So it's basically the natural reaction of that plot over a long period of time.
Actually, and those the data that they saw are actually Larry Woolbright's data, which are not collected in the LFDP. Just to be scientifically correct, his two plots are right in this little area near the suspension bridge.
Oh, okay.
So he has his own plots. He doesn't. Some people collect data. You're correct. Some people collect data in this LFDP, and we've collected some Coqui data. But early on, he put two plots down here near the suspension bridge, and that's where he's collected most of his data. But your statement that it's unmodified forest with no human impacts is correct, and none of these treatments. Okay. So we started this experiment back in 2002. It's about 4 years after Hurricane George. The forest was coming back together by that point, but we followed the plots for 2 years so that we could better detail the impacts once they were in place. So there was a pre-treatment measurement period, which as ecologists understand. And then we hired these arborists, and these guys are amazing. I've had them out to my house working, and they literally get a rope up in a tree, they climb up into the tree, and then they cut the biggest branches off. They cut the tops off the palm trees, just like happens in a real hurricane. And then they throw a rope and get into the next tree and repeat that. And they actually spend hours in the forest canopy going from tree to tree without ever coming down to the ground. And so we use these arborists as our hurricane, and they can try to remember from the last trim. I think they could pretty much go through one whole plot or half a plot in a day. They work fairly quickly. So you can see this guy in the upper left has a long saw, and he's cutting the fronds off this palm tree, which happens in a hurricane. And then this guy has a smaller tree, and he's cutting that off at 3 meters because most of the impact of the hurricane winds are higher up in the canopy, and there tends to be lesser impact below, basically about head height. And so we cut all this stuff off, put it on the ground, and the forest plots looked like that after they were trimmed, which is a pretty severe hurricane. But you can go look at that and go back to this picture in the upper right, and you can at least see the similarity. And you can also see here that it's a lot of in the understory. I mean, there's a lot of green stuff because it's knocked down, but it's mostly the stuff higher in the canopy that's damaged. So we tried very hard to mimic the impacts of a hurricane. And then we do this with an army of volunteers, and I can't believe these kids still come, because basically what I do is I give them a plane ticket, and I say, you're going to come and do all this dirty, grubby work, and I'm going to give you $15 a day so you can buy food and give you a free room or free bed in a dormitory at a field station. And kids come down and do this. So this is 2 of our volunteers. All of this material, they had to weigh it to determine how much was cut down. And then for the treatment where we removed the detritus from one plot and placed it on the other, they literally had to carry all this stuff. And it's literally tons of material. They have to go from one spot to the next. Now, in one case, the pictures you see before us, the 2 different plots were across a stream, and being smart kids, excuse me, they strung up a wire and just slid this stuff in a tarp from one plot to the next. But the original treatments at all the plots took about 4 or 5 months to put in place. We had to sort all the material. There's your 11 metric tons per plot, and I can't remember. That's maybe twice as many tons in regular European measurement. You can see all the material. A lot of the larger sticks, ecologists call coarse woody debris, and the leaves and stems or small sticks are called fine debris. They have different impacts as they decompose. That's why we distinguish them by size. And then after we sorted and measured it all, we finally could spread it out. And you can see how much material went on the forest floor in these plots. It was a lot. So I'm going to, at this point, show you data on the impacts of this trimming experiment. So one of the things that we wanted to affect was canopy openness. And the way we measure that, you can see it on the left-hand side, is we have a camera that has a hemispherical lens on it. It's basically a 360-degree lens, goes from horizon to horizon. Below is one of our control plots, so you can see all the green leaf material. And then above is one of our trimmed plots, where you can see the canopy openness that was caused by the trimming. The graph compares the trimmed and untrimmed plots. Here is the original data before any trimming was done. There was about 10 or 11% canopy openness, which is kind of high. It's probably the result of the fact that there had been a hurricane here 5 years before and the canopy was still closing. But then here you can see when we trimmed the canopy, we got about 16% canopy openness, and then the other plots continued to decline, and I think that's because of the recovery from Hurricane George. And then the canopy closes fairly quickly. Over about a period of 2 or 3 years, something is growing back, and that was one of the questions we wanted to answer. And then here's the detritus on the ground, which I've shown you here, 2 sizes of dead wood. We're interested in dead wood because it's something that decomposes very slowly and actually has a big impact on soil ecology. I'll just leave it at that. So we wanted to see, so we've measured the percent cover of those over time. Obviously, when you put a lot of dead wood down, the numbers go up, but then you can see this decreases as things decompose. The larger pieces of dead wood went up with the manipulations and decreased more slowly, and we're still higher 3 or 4 years later than the plots where we did not put any debris. So these are the 2 major things that we wanted to impact: canopy openness, debris or detritus on the ground caused by the hurricane. And I had another graph. Sorry, these are out of order, but that's okay. This is, well, now I'm confusing myself. Let me get back. Okay. This is litter depth. I mean, this is literally in those plots taking a ruler and saying, how deep is the litter? And after we piled on all that litter, of course, the litter depth went much higher. And so there was actually, that's the fine litter that we're interested in. Just to then compare these numbers to those numbers that we collected in real hurricanes, we put together this little table. So here's canopy openness between our canopy trimming experiment and one other hurricane. This is fine litter, which is leaves and twigs. Coarse woody debris, which is just basically sticks and logs. And then litter depth, measuring the depth of all of that litter with a ruler. Canopy openness and the CT was 16%. A real hurricane, we had a number that was like 27. So we didn't get, as much as we trimmed from those plots, we didn't get quite the same canopy openness, but we got a lot. The fine litter, the number we had from Hurricane Hugo was 1,934 grams per meter squared. We came very close, 1989, for our experiment. Coarse woody debris, we went a little bit high, but we got, numbers that are reasonable for a hurricane. And the litter depth post hurricane also was a little higher than we measured before. But again, we're getting, numbers that are realistic. So, on this basis, we're pretty pleased with ourselves that we were able to actually mimic a hurricane. Okay, I'll quickly summarize some of this. So I'm a forest ecologist, and so I've analyzed a lot of the data on the responses of the trees and ferns and seedlings. Um, and I could show you a lot of graphs. I'll show you a few, but here are the basic responses. When you place debris, hurricane debris and detritus on the forest floor, it buries a lot of seedlings and ferns and other herbaceous plants, and it causes transient mortality. That is, it kills a lot of the plants that are there. And this we predicted from our knowledge of previous hurricanes. There's a lot of seedling mortality caused by being buried in the debris, and so we were able to show that happened again. But that's a pretty obvious one. Over time, the canopy removal caused the increased establishment of fast-growing pioneer trees. Pioneers are species that whose ecology allows them to respond very quickly to disturbances like hurricanes. Around Chicago, if you know what sumac is, it's a kind of red leaf plant that comes in um, um, abandoned agricultural fields. That's another example of a pioneer species. We have our own. And they come in like gangbusters after a hurricane, and they did that after our simulations. And then when you put that detritus on the ground, what I call detrital inputs, what a scientist would call detrital inputs, that stuff decomposes and it eventually releases nutrients back into the soil, and that actually helps the trees that are there. So um, while a hurricane might seem like a great disturbance, and it certainly is in the early months after the hurricane, there are processes that decompose that material, return the nutrients to the trees, and actually can have positive impacts on their growth. So this is a graph showing the seedling mortality, mortality of seedlings greater than 10 centimeters. The open symbols are where we dumped debris on the ground, and the y-axis is actually rate of seedling mortality. And so you can see between 2004 and 2005, separated by the arrow when we did the treatments, there's much higher mortality. After that, there's no changes or effect on seedling mortality. Other factors take over again, and that's why I use the word transient. The mortality impact is transient. If you look at the number of trees that are in these plots, the differences in these two sets of graphs, the upper ones, this is the effect of canopy opening. This is all these little pioneer trees coming in and filling up the open areas and explaining why the canopy closes so quickly. And here they are. These are our little pioneers. This is a species called Yagrumo, which is also in Journey to El Yunque. There's another one, some larger ones. There's another species called, I'm actually blanking on the name. I'll think of it in a second. But it's another pioneer shrub that comes in very quickly. And this is what's filling in these plots, and actually happens after a hurricane. And that's what's closing up the canopy over time. Okay, getting back to the frogs, we've published one study on the effects of the treatments and the canopy treatment on the frogs, and this was done by Paul Kowinski, who teaches at a little college in the Midwest. He comes down twice a year, measures the frogs. This is the first year of data, so you can see there's the two pre-treatment measurements he took up until January 2004, and then afterwards. And then the two graphs compare debris and no debris added, and the differences here aren't that great, which is interesting because we think debris is important in the long term. But then the open bars here are the trimmed plots, the closed or open symbols. The closed symbols are the untrimmed plots. And so actually the number of frogs went down with canopy openness, indicating probably that it was very hot in this first year of this treatment. It was very hot and very dry, and they probably migrated out of the plots, would be my guess. So there is evidence that they avoid the canopy opening to the degree that they can. And at least on the short term, this is only first 12 months, we're still analyzing the data from the remainder of it. Okay, and then here's a picture of all our volunteers. This guy here is Aaron Shields, who worked for us as a technician running the project. He's now a scientist working for the USDA National Wildlife Center in Nevada. He was out in Hawaii for a long time and continues to work with us. And there's a whole bunch of folks in here that this is Chelsea Prather, who is a graduate student working on the project. She now teaches at the university. She teaches at a university in Virginia. So those are some of the folks that worked on the project. So at that point, I can take some questions or take comments, whatever you'd like to do. I can go back over some things if people are interested in doing so.
All right, thank you. Any questions, comments?
Curious about the data, again, of the number of frogs for each one of his controls versus each one of his manipulated things. I'm not sure I understood that. I know the greatest amount was the one where it had no canopy and more trims on the ground. But what were the other ones in relation? Like how close were they? I guess I kind of missed that graph.
Can you put up the graph, the cookie data? And unfortunately, our overhead screen has a bunch of dots on it, so it's hard to see the data. So maybe you can draw.
Okay, that's pretty thin to begin with.
Yeah.
So you all can see the red line, right? This is when the treatments were imposed. Is that correct? Can you see the red line, Stephen?
Yes, and then there's two. So the red line on the left represents the plots where no debris was added, and the plots on the right with the red line is where the debris was added.
And what's the number of cookies? Like I can't read. How do I read that?
Oh, so on it's the number of frogs.
Frogs per hectare.
So on the x-axis, it goes from 0 to 8,000 frogs per hectare.
Yeah, we're just expressing that on a common area. The size of the plots is about 1/10 of the hectare. So the numbers are actually 1/10 of that. But to compare to other studies, we express everything on a per hectare basis, just as a standard.
And then
for standard to compare.
For each of the data points, is the line through the data point, is it the error bar? Because you're averaging across 3 plots.
Right, those are error bars.
Went down, up, down, up, down. I'm reading the frogs go down, up, down, up, down, up, down.
Right, so they kind of go up and down over time.
Right, what would be the reason?
So the question that's being asked is why are the frogs going up and down over the year? Now, are you counting? Is this both adults and juveniles?
I'll have to look at the paper. I've got it right here.
In the Journey to Yunque,
that would provide an answer. Let me.
Just the stuff we look at is just adults.
It's just adults, yeah.
What constitutes an adult 1 year old when they can reproduce?
Jess, what constitutes an adult versus a juvenile? Is it 1 year old?
I think it's a minimum size. Lower size limit of an adult is 2.5 centimeters, about an inch.
Well, I guess you
Yeah.
don't. Although I could see that being in his newspaper, first day
So one of the teachers said, that makes sense because we can't ask what their birthday is.
This combines data. I just quickly reread the methods for the paper. This combines juveniles and adults. And a lot of the bouncing up and down is probably because of changing juvenile numbers. Adult populations are fairly stable, and the juvenile numbers change a lot depending on how wet or dry it has been. So a lot of that jumping up and down, I bet if we put a graph, some kind of graph of rainfall on there, I bet this period here where they declined probably followed a dry period. I bet this June or July was fairly wet, which is why it went fairly high. So, but what we're seeing is against the background of all that up and down, there's clearly a difference between the canopy opening treatments, whether there's debris or not, later in this period.
The spheres that are open, are those the ones that has the canopy opening versus the black dots?
Correct. So this is really on the short-term data is really saying they don't like the effects of the canopy opening. Now, different from a real hurricane to a degree is in a real hurricane, they can't get away from the canopy opening. And these animals will move meters, not kilometers or not, and not hundreds of meters, but they will move meters and they'll tend to migrate away from some place that they don't like. So there may be a little bit of some with animals that are real, that have the ability to move. Scientifically, we call that agility. Doing an experiment on this small an area is problematic. And for example, we didn't bother to try and measure the responses of birds because they move around a lot. But frogs have limited movement. You might expect to see some impacts, but these short-term trends are a little bit hard to interpret. But if what we have in the CoKey module is correct, we would expect the graphs on the right to go up and stay higher than the graphs on the left, because we're arguing the outcome of the module is what we understand. The outcome in the field is that there's all this debris for them to hide in. So I would expect the numbers on the right to go up over time over the next 2 or 3 years in comparison to the graphs on the left.
Okay, we had another question.
Does the temperature affect, like I see in July, that spike, like what's the temperature range there over the course of that March, July? Like what's the temperature like in the March?
So the question was,
what's
the range over the course of a year in the rainforest?
The temperatures in Fahrenheit at this time of year in the forest, I would say, are in the mid-70s, whereas in the summer, and under the shade of the trees, are in the mid-70s, in the mid-80s at the beach, and in the mid-80s in the forest in the summer, and kind of in the low 90s at the beach. So it varies. I'm actually converting centigrade to Fahrenheit, but it varies 8 to 10 degrees Fahrenheit during the year. So this July measurement, it would be pretty warm and decreasing over the next 6 months from there.
So how much does that cycle of temperature affect the CoKey population?
I don't think it would have a demonstrable effect on the numbers over time. They may be, it's hard to say. They're certainly more active when it's warmer, but they may create more metabolic demands on their food when it's warmer. So I wouldn't attribute that jump in numbers to anything having to do with temperature, but it could be a contributing factor.
Overall, his data shows that more debris added has not increased population. He's saying his hypothesis is that the number will go up.
Well, so this is 1 year of data, and in you'll notice in the Journey to Yunque, it was after a year that it really started to spike.
So this is just the most recent data that he's showing.
Well, it's the most recent data they've analyzed, because it's the first year of the Canopy trimming experiment, which was back in the early 2000s. So as they continue to analyze more data, you might begin to see that effect.
You might not.
Or you might not. That's why you do the research.
Or you might not. Yeah. So
another question?
The pattern that we can look at the CT data we haven't yet for the frogs is this curve B that I was talking about. And the time span is 1 to 5 years that this increase occurs. And so if you look only in the first year, particularly with all the other things going on, you might not see that effect. But you're absolutely right. We're not in this experiment confirming the predictions from our previous experience.
I think I just saw the slide. I think earlier you gave a presentation. Didn't you say that the debris killed off the other species?
Yes.
But then in our graph, right, plan.
But that was 3 years later.
The older plants, but he said the new.
To what extent are you seeing, so you mentioned in the initial debris infusion that it killed off a lot of the understory plants. How quickly did you see those recovering in the plots that had the canopy opening?
Fairly quickly. Trying to see.
We have in the 3-year illustration, we have a lot of understory growth of shrubs and heliconia. And so I think the question is, are you seeing that repeated here in with the canopy trimming experiment?
Yeah, we are. That's what we're seeing, is that picture right there. Is that answering the question, Stephen?
Yes, although we're not seeing the heliconia plants, but this looks like it's a little bit taken towards at an upper angle.
Right, and you're seeing agrumo and a species of Psychotria, not heliconia.
Right.
But a profusion of growth.
So can you speak to the discussions about how frequently the program intends to continue doing the canopy trimming experiment?
Oh, right. I was actually had intended upon throwing in a couple of slides. So this past year, or a little over a year ago now, we repeated the basic trimming. Well, in the hurricane simulation. So it was a lot of work to keep track of these treatments where it was a lot of work to establish the treatments, where we cut all this material out of the canopy, gathered it up, and moved it to another plot. And we learned a lot in the first 10 years after those first set of manipulations. So we decided to carry on this project to look at what would be the changing effect of the frequency of the hurricanes. We're going to repeat the basic hurricane simulation every 10 years. So when you looked at the graphs, you notice that we did the last simulations starting in 2004, finishing up in early 2005. So in late 2014, we redid the manipulations in the hurricane treatments. So we trimmed the plots again. They looked the same as they did before. I couldn't find any pictures to actually distinguish this trim from the last one. So we're going to repeat this every 10 years. Our real focus now is on what happens to the soils. Are they going to increase in carbon content because you're dumping this decomposing material on the ground every 10 years? Or are you going to get no effect because the soils are warmed up and they decompose rapidly, and that carbon material is actually decomposed by microorganisms and converted to carbon dioxide and leaves the soil? So, and that's been our long-term hypothesis has been that you're going to change soil organic carbon because you're repeatedly trimming. It's like mowing your lawn a lot. If you mow your lawn a lot, it increases the carbon in the soil because you're constantly cutting the grass off and letting it decompose and moving that carbon into the soil away from the grass itself. And so those basic principles underline, it's a little bit more sophisticated than that, but not too much more, that we're going to change soil carbon. And so we're doing a lot of detailed soil studies in the context of the most recent trim. I mean, I guess for me, the big question is whether I'm waiting around for the next set of trim in 9 years. I'll be 66.
So are you also hypothesizing that there would be a change in the distribution of tree species?
Yes, correct. Because the original trimming or any hurricane-like disturbance promotes the establishment of these pioneers like the ones you see in front of you. We expect there to be a shift towards those kinds of species in the plots, and that's actually going to change. They're actually, because they're so fast growing, their wood is weak, and so they're actually more susceptible to hurricane winds than the slow-growing species that are usually there. And so that's going to change patterns as well of damage as well as the species composition.
Any last question?
I don't know if you mentioned it, what do you want to do with information today?
So where do you share the information that you learned from your experiments?
The detailed information comes out in scientific publications, so I can show you. Let's see if that. Can you see that, Stephen? This is an entire.
Well, because your video is pretty small. Forest ecology.
So anyway, I'm trying to show you a journal that I've been working out of, and that's an entire set of 14 publications on all different aspects of this experiment. And so that's one way we share it. You can find summaries of this experiment on our website, but quite honestly, our website could use quite a bit more development, something that we're working on right now. Those would be your two primary sources of information on this experiment.
So do you know off the top of your head, at a rough estimate, how many journal publications have been published about Luquillo LTER?
The Luquillo LTER?
Yeah.
I think we're up over 900 publications, as I recall. That's 900 publications over a period of 25 years.
So another way, and I think what part of the question is, so how does this information from the experimental plot inform the management side of El Yunque?
The short answer, I think, is not as much as we would like it to. The slightly longer answer is that in the last 5 to 10 years, particularly on the streams and wildlife side of things, there's been a lot of effort by the managers of El Yunque National Forest to talk to the scientists in our LTR and engage them in what these impacts to some of these disturbance are, what are the major management issues, and how do you use the science to manage in a better way. But this is actually kind of a new thing and something. I mean, we've all become kind of friends now as we've all worked together in the same spot and we're talking and sharing information a lot more. But it's not done as well as it could be.
All right, thank you, Jess.
Okay, thank you.
Bye-bye.
See you later.